Hello again. Now we'll be talking about the beam load calculation. Again, this is the structural design for Architects 2 course by myself, Dr. Mohammed. So, before calculating the loads, we need actually to understand the concept of the beams. The beam is the main element transferring the load from slabs to the columns. So actually, because of that, it has a significant depth and of dimension called t, and the width is b, and uh, based on that, based on the span, we'll start calculating the optimum value of, or the most convenient value of the beam depth t. So if it is a cantilever, we are talking about a range between 1/5 to 1/4 of the span. If it is simply supported, it's between span over 10 and span over 8. And if it is continuous, we are talking that it's somewhere between span over 12 and span over 10. But it should always be in multiples of 50 millimeters because I mean, having a beam as 706 millimeters is not practical at all, because the increments of 50 millimeters, these are the increments that the carpenters use when they work on the formwork. So loads acting directly on beams are mainly due to the big chunk of it is due to own weight, the dead loads. Dead loads, whether from the beams or from the slabs or from other elements. So if we are talking about the own weight of the beam, the own weight of the beam is mainly the cross-sectional area, which is the width b multiplied by the drop thickness, which is the t minus the thickness of the slab, multiplied by the density of reinforced concrete, which is actually 25 kilonewton per meter cube. The own weight of the wall, again, it depends on the unit weight of the wall itself. It depends on the plastering, and it's mainly also depending on whether you are transferring the whole load of the wall to the beam beneath it, or part of it will go to the columns through this configuration that you could see on the right hand side. However, it is more conservative to consider that the beam will carry the total weight of the wall. So in addition to all of that, you are receiving loads from the slabs, and whether or not you are talking about loads received from the slabs in whatever direction, this will depend on actually the system of the slab from the first place. I mean, if we are talking about a two-way slab, it's totally different than a one-way slab. In a one-way slab, it's more direct. You have only two opposite beams that will carry the load of the slab due to the slab having one dimension more than double the other dimension. So in such a case, I mean, the distance, if we're talking about the upper slab, the distance B between A and B is more than double the distance between A and D, which is the dimension called L1. So L is more than double L1. So in such a case, it's acting in one way, so it's throwing the loads on these two opposite beams, beam AB and beam DC. So it's simply throwing half of this on one direction, on one beam, and half on the other direction. So simply you're having the dimension L1 over 2 multiplied by the pressure, whether this pressure is coming from the dead load or from the live load. And once you get this thing, so you multiply it and you get your load acting on the beam. And of course, if we're talking about the dead load, so we're talking this is the thickness multiplied by gamma concrete plus the flooring weight. What if we are talking about a two-way slab? So sorry, this is a typo here. It's a two-way. It's not a one-way slab. So if we're talking about a two-way slab, this two-way slab, that means that here we have one dimension which is less than double the other dimension. Okay, so that means that we'll start distributing the loads on each. So one will have this trapezoidal load acting on it, and the other will have this rectangular load acting on it. So it's not just this triangular load. It's not just a rectangle as previously said. So here, to make life easier, if you're doing calculations by hand, it's easier for you to get the equivalent uniform load instead of having a trapezoidal load or a triangular load. It's easier for you to deal with a rectangular load. However, actually, if you are modeling this thing on a software, on a finite element program or whatever type of program like SAP or ETABS or whatever, and by the way, a lot of them actually are connected to BIM softwares like Revit, so they could easily transfer the loads from here to there. You could easily do the thing. If you are doing this, actually, this would be much easier for you. I mean, much easier than this exercise. However, if you're doing the calculations manually and you need to design for shear, you will use a coefficient called beta, or if you are designing for bending moment, you use a coefficient called alpha. So in such a case, you will be spreading, or instead of having this triangle, you are having a rectangular load. Instead of having this trapezium, you are having a rectangular load, whether this is for bending or for shear, and these values will differ from one ratio of long dimension over short dimension to the other. So you could see if it is a 2, you started to be going towards actually being approaching the 1, which means that it's nearly a one-way thing system. And again, these rules apply only if it is only one triangular or one trapezoidal load covering the full. The simplified analysis, again, if you are talking by doing calculations by hand, it's easier to do simplified analysis than doing anything else. But for us, the simplified analysis is more convenient. But if you're using a computer software, it makes no difference, because the computer will do everything for you. It will give you the values for the bending moments and the shear forces and all what you need to make the design if you want. So this simplified analysis is based on a certain condition that you need the spans to be nearly equal, or the maximum difference between them is 20%, and the loads all over to be nearly equal, or the maximum value, the difference between them is to be within 20%. So in such a case, if you are satisfying these conditions, the moment is equal to simply W over times L squared over Km, and this K will change depending if it is continuous from 2 spans, 3 spans. The value of K will change from the mid span to the support, and so on. Same thing for the shear. Here you have Ks times W times L. So this sometimes it's 0.4, sometimes it's 0.6, sometimes it's 0.45, depending on the condition.